how do you reinvent the circuit breaker? It's something that's been in existence for decades or even a century, kind of back to the times of Thomas Edison. And now miniaturize it, make it smaller, put it on a new platform, enable applications that you couldn't do before. That's what we were doing. And that's really how this MEM switch technology got its start.
From EE Tech Media, this is Moore's Lobby, where engineers gather to talk all about circuits. I'm Daniel Bogdanoff. Today in the lobby, we're exploring the tiny technology that can switch big wattage. Our guest today, Chris Keimel, is the CTO and co-founder of Menlo Micro. They can trace their technology roots all the way back to Thomas Edison. Menlo Micro came out of a decade-long research effort at General Electric's Global Research Center before striking out on their own to develop MEMS switches that can handle milliwatts to kilowatts at DC to gigahertz switching frequencies. These micro-electromechanical systems are an astounding feat of engineering, and our guest Chris is at the forefront of this tech. Chris, thanks for being here. I'm really excited about this one.
Oh, no, Daniel, thank you. And thank you for the interest in what we're doing at Menlo and our MEMS switch technology.
So how did you get into technology and engineering? Is that something you've always wanted to do?
No, and engineering was something that growing up, I just never had the idea what an engineer was. If you asked me what an engineer was, I'd say, hey, the person who drives a train. I always had a soft spot for animals and maybe even one day being a veterinarian. But unfortunately, I found out that I was highly allergic, and that pretty much squashed my aspirations for wanting or dreaming to be a veterinarian, because that just wasn't going to be a good combination.
So you switched it up for engineering. What does engineering embody for you?
To me is just it's tinkering, it's toying with things, it's figuring things out and just being creative. And that was me. That was whether it was Legos, Tinker toys. I think even probably when I was in second or third grade, I made this Tinker toy contraption that I thought was controlling this massive snowstorm we were having. And that was just me and my imagination. I always had that imagination and tinkering kind of in me. And then it just naturally led down this path through school and high school of, hey, math. I love physics, chemistry, bringing on more of it. And that just translated into combining those interests together. And I always go back to, and I always tell this story to kind of young engineers and people in high school about who want to ask questions about careers. And I always tell them the story of my father and how I always remember this when growing up. He told me, do what you love and the rest will just follow. And what he was really getting to was, it doesn't matter what you do, what you want to do, just enjoy it, love it. Every day, if you get up out of in the morning and get up out of bed, and you want to go to work, you can't wait to try something new. You can't wait to just tackle what the day is going to bring. And hey, you know what? You're going to be successful at whatever you do. And I think that's that describes engineers. That describes really everyone. And I just took that to heart and followed what I wanted to do that day. And that just took me down this path of engineering, from tinkering to building Legos, to high school, to college, and where I am today.
Did you focus on semiconductors in college, or how did you end up going down that route?
Yeah, that's a great question, right? Like, how does one get into semiconductors? And it really, no, it wasn't a focus in college. I didn't really know what engineering was. I took college as this exploratory experience of just, I think I like tinkering. I'm good at math and science, thinking about going into engineering, but oh my goodness, there's chemical engineering, mechanical engineering, electrical engineering, material science, and all of these. For me, it was a trial. I followed this path of trying what I felt my interests were and trying to figure my way and figure my life out. That led to me really one day going up and hey, I like this material science class. I like what this Professor Chris Ober, what he was teaching. This was as a freshman. And I said, hey, you know what? Can I work in your research group over the summer? I'm going to be on campus. I was on the crew team and rowing. I was training over the summer. And I was like, hey, can I work in your group and just understand more about what goes on in developing polymers? And he just happened to be working in a group that was doing polymers for next generation at advanced lithography. This was back in the 90s. And that just got me down this path of saying, hey, this is interesting. This is I enjoy this pathway for semiconductors. I enjoy making things small. I loved computers as a kid, and this was just that connection into computers and that concept when I was a kid of like, oh my goodness, how does my Mac Classic, how does this Commodore 64 even work? How does it save data? What's going on inside? And this just, that class and then this concept of working in the fundamentals of making things small, making things nanoscale in feature to make computers faster, more memory. That just appealed to me, and that's kind of how I got started.
Do you have a model of computer that you're most fond of? Kind of like a retro corner in your house, maybe?
Yeah, I do. I actually do have a functioning Mac Classic. This was my parents bought this Mac Classic, I guess the 80s, right when it first came out, 80s, early 90s. And it still works. I still was able to network it in the house. So it's there. It's chugging away.
That's awesome.
I think all 8 megahertz of it.
That's fantastic. So when I think of lithography and semiconductors, I don't really think moving parts. I think everything's in my brain, everything's just kind of static. So can you explain, just give me an introduction into the world of micro-electromechanical systems?
Yeah. So what's interesting about MEMS is when you think about nanos, first of all, you think about these computers and CMOS and memory and right, Moore's Law, the push towards ever scaling features. Well, that's very real. That's very true. That's happening. And there's a huge industry push behind that. Actually, what I love about the MEMS space is that it's leveraging off of legacy equipment, legacy lithography. Lithography is the patterning, is the technology around how do you take these features and put them on a wafer and use that to etch materials, etch metals, pattern metals, make your features that make these integrated circuits. What I love about this connection between lithography and MEMS is that, the feature size is less important. What's really important is the interfaces, the materials, the stresses, and how you build up these layers versus how small can you make these layers. And going through undergrad and grad school, I was always involved in making things smaller and smaller and smaller. And then I got into my career and I started working on these devices in the MEMS space. And I was like, oh my goodness, I'm working on microns now and not nanometers. But it's the same processing, it's the same techniques, it's the same materials. It's just now using them in different ways and leveraging different aspects of those materials to make something move at the micro and nano scale to to make a sensor, to make a switch.
So after school, did you jump right into this, or what was your first job out of college?
Wow. Yeah. First job out of college. Well, you know what? It was with GE. Right out of grad school, I went to GE's Global Research Center, and to me, it was this great opportunity about how do I take everything that I'm learning in school and apply it, and how do I apply it? And what I loved getting started at GE was they were just getting their nanotechnology program started. This was in the early 2000s, and it was how do we make quantum dots? How do we make optical waveguides? And so my first role there was, hey, how do we make optical waveguides and create these optical light pipes? And how can we make information travel faster on computer chips and start creating some of that fundamental technology? I had never done that before. I was always trying to make things smaller and smaller. And all of a sudden, again, now, wow, it's taking those same types of learnings and processes and failure analysis and now applying it in a completely different space. And I loved it. I loved that ability to explore and invent and create. And GE and Global Research Center, they just gave me and the thousands of scientists there that opportunity.
When I think about GE, my brain goes to high power, big things, not necessarily small footprint like microelectronics. Did you do high power design work there too?
Yeah, that's a great question because you think of GE, jet engines, appliances, turbines, big, powerful systems that move and power the world. what we were doing there, and the role of us at the research center was to bring new technology into these businesses that created these big, powerful systems. But how we got this switch technology started and why the interest in nanoscale features and let's say nanoelectronics or MEMS was really about these systems need controls. These systems need to distribute their power. They need to control their power. And the purpose that we were serving was to invent these new technologies that weren't out there on the market, that you couldn't either partner with companies to develop. It was all about bringing new capabilities. And that's how we actually got this switch technology started. It was this idea of how do we reinvent the power controls and distribution system, right? How do you reinvent the circuit breaker? It's something that's been in existence for decades or even a century, kind of back to the times of Thomas Edison. How do you reinvent that basic fundamental technology and now miniaturize it, make it smaller, put it on a new platform, do things with it, enable applications that you couldn't do before? That's what we were doing. And that's really how this MEMS switch technology got its start and how it eventually transformed into Menlo Microsystems.
We'll hear more about that in a second when we return with Chris Keimel, CTO and co-founder of Menlo Micro. This episode is sponsored by CUI Inc., a Bell Group company. They're here to deliver power when you need it. As a leading provider of AC to DC and DC to DC power supplies, CUI Inc. is dedicated to offering choice, reliability, and ease of access to their products and first-class service. Their goal is to assist you during your design process and provide the right power supplies for your consumer, IoT, medical, and industrial designs. CUI Inc. products and resources can be found through their diverse distribution network or at CUI.com. And we're back with Chris Keimel. Chris, I'm curious, why switching? Why are switch architectures so important in semiconductors?
Yeah, so that's such a great question because it's everything that's hidden. You think about the world today, and when we wake up in the morning, we turn our alarm clock off, our lights turn on, the coffee pot turns on, the car turns on, you turn on your windshield wipers, you open your window. There are switches and power controls around us every day, and we almost ubiquitously, we're just using it. And that's what really intrigued me. That's what I love about this technology is I get to have an impact on developing a technology and looking to transform a technology that we use every day. How do we reinvent the switch? How do we reinvent the control of everything that's electrical? It's the interface. The switch is the interface between us as humans in a society and the electrified world. That's what it is. It's the interface. It's the controls. It's how we can bring smarts and this concept of the industrial Internet of Things and the control of the power systems. This is at the heart of all that, and that's what drives me to develop this technology, to invent, and to really help push this forward and have an impact on the world.
Can you explain for me what is MEMS and how does it work?
MEMS. So first of all, MEMS. What does it stand for? It's micro-electromechanical systems. The way I think about it is, it's really at a high level, it's the interface of actions and electronics. It's the interface of how actions are sensed, how things are controlled, and how they then really interface with the electronic world or let's say the current or the signals. And so a MEMS device stands at that interface of sensing and controlling the actions of the world, whether it's a switch and a circuit, or an accelerometer and an airbag, or a inertial sensor and your navigation system. They're all at those, right? It's that interface between us and the electrified world. And I think the really cool thing about it is, from a material scientist perspective, the semiconductor industry has been fantastic in developing all these tools, these fabrication processes for CMOS and memory and pushing that to great scales, down to nanometer level nodes. The MEMS industry takes advantage of that. We don't necessarily need those small scale feature sizes, but the same materials, the same processes, that same foundation is leveraged by the MEMS industry. So it's this kind of like the symbiotic relationship between, on a processing, on a fabrication and materials perspective, right? It's a symbiotic relationship with the semiconductor industry to make these types of devices using that platform.
So it's like for a relay, you have basically an electromagnet throwing a little metal, arm to make a connection. How does a MEMS device switch work, like on silicon? What are kind of the nitty-gritty details?
These switches are operated electrostatically. So what does that mean, right? When it's operated electrostatically, it basically means that if I take a voltage and throw some charge on a pad that's just sitting maybe a micron away from our this mechanical cantilever, that cantilever attracts. It's the same principles as taking a balloon, rubbing it on your pant leg and taking it up and putting that balloon next to your hair, right? Your hair sticks up because all that charge that you transferred to the surface of that rubber balloon, it creates a field. The same thing happens here. We're pushing a few electrons onto a metal gate, and that gate sits about a micron away from our switch, and it pulls it closed. And the same thing is, once you remove those electrons, the switch opens up. It has this, it's sort of like a spring. It's got this mechanical restoring force that opens it right up once you remove that charge. We know from the electronics world, right? We can move charge in nanoseconds. In this case, mechanics, it's a little slower. The switch responds in about a microsecond. So we can move charge really fast, but the switch it's a little slower to open up, and it'll respond in about a microsecond.
So if it's a mechanical restoring force, I assume there's some like advanced material science to make that happen. I'm picturing just like a leaf spring or something almost. Is there like a number of switches it can go through, or a length of time it can stay actuated, for lack of a better term?
Yeah, so there's really two aspects, right? It went from a springs wear out. And in this case, yes, switches will wear out, but what we've developed, and really the secret sauce behind the switch technology, is in the metallurgy. It's in the material science of how do you make something not wear out? How do you make something not fatigue? How do you make something not creep when it's undergoing motion and cycles, or being, as you described, or being held closed? So what we've done and developed and innovated around, and that's done a little differently from the semiconductor industry, is we've employed alloys. Alloys tend to be the best of both. You try to get the best of both worlds in an alloy by combining different materials. And so we've combined materials together in these alloy formations to make our mechanical structures. And that allows our mechanical structures to resist that deformation, to be stronger, to allow it to operate instead of mechanical relays today operating hundreds of thousands of times, or maybe a few millions of times. Our relays mechanically can operate billions of times without degrading their performance. And it's those innovations that allow us to develop these really tiny relays and not have them deform, not have them fail, have them be reliable, robust, and provide that same level of performance of a mechanical relay, but do so with orders of magnitude more operations and cycle performance.
So are these relays physically switching, or are they more of a like electrophysical device?
No. Yeah. So we're making an ohmic relay. And what's great about an ohmic relay, and really this metal MEMS process, is that it's made of metal. It's purely conductive. And we do this on glass substrates, purely insulating. So we're creating this platform that allows the construction of relays for both the RF communication space and the power space. What that means is, and we always talk about this, hey, this switch has the capability of DC to light. Well, what does DC to light mean? It means that the power, the energy that's transmitting through the switch, that the switch can control, that it can open or close it, is DC all the way up to tens to maybe 100 gigahertz. So the switch doesn't open and close at that frequency, but the signals going through it at these ultra low losses are transmitting through this switch, and the switch is controlling whether the signal gets through or whether it's blocked.
Was MEMS switching something that was just kind of a brainchild of someone and was then searching for an application, or was it really driven by like an identified need? Like, I need to be able to switch these things, but smaller.
Almost no one in their right mind would combine this mic. Let's go make a circuit breaker smaller, right? The entire industry was saying, if we want to put more power through it, we got to make it bigger, more metal, make it bigger, make it beefier. That's how you handle power. This was thinking outside the box. It was the business saying, how do we want to reinvent this? And part of the research center's role at GE at the time was every business unit had to have 2 or 3 technology thrusts that they wanted to transform their business. So it was a business push. And then the research center responded and said, okay, what technologies can we put at this to do this? And it really was, okay, we think we could make this MEMS switch concept of, hey, if we make it smaller, if we make it faster, we can overcome some of these limitations that the bigger switching systems, the mechanical relays have. And it was really that out of the box thinking, and you know what, not being too wrong in that thinking, that got this going. And then the more we dug into it, the more we looked at it, and the more we uncovered, the more we said, hey, we think we can make this work. And it does seem feasible. But there's still a long road ahead. And at the time, the business was supportive of that. They didn't need a solution in 1 year, 2 years. They were willing to wait the multiple years to develop a transformational technology.
Is that normal at GE, where there's a business unit looking to solve a problem, and then there's a research arm that's interfacing with those teams?
It's atypical, I'd say, in the world that we think of today. Everyone wants things now. They want things yesterday. They want things sooner, faster, cheaper. The world that when I started at Global Research in the early 2000s, there was a big push from the business unit. It was every business unit, the energy unit, the industrial unit, the healthcare unit. It was investing in 2 or 3 transformative technologies and leveraging this collaborative research center of 1 to 2,000 scientists and experts in their field to come up with the ideas, the out of the box ways of thinking and applying solutions. That was the environment then. And quite frankly, when I look back at it, this switch technology, what we were going after, just never would have been born without that type of industrial research leadership of dreaming big and then putting the people together and allowing the people from multiple disciplines to go together and develop and invent a technology like this. Because we're talking about a MEMS technology here, and there were not a lot of MEMS people on this program. There were maybe 10% of the team of 20-person teams had MEMS experience and background, and me not being one of them.
That sounds pretty terrifying. What were some of the early challenges you faced?
I'll just say one of the first challenges was, hey, we think that this tiny little switch can have an impact. What does it look like? How do we make it? We started scouring who was making MEMS relays, how were they doing it, what technologies were they using, and even just working and partnering with some companies at the time to sample what they had. And what we found was that none of the universities, none of the early companies or labs that were looking at this technology were really looking at it from a power perspective. And that's when we started pushing watts or tens of watts or hundreds of watts through these relays. We were just blowing them up in the labs. And I'm like, okay, this is a transformational moment. We either stop and move on to something else because this is not going to work, or we dig in and we figure out why this is not working, what needs to be updated, what needs to be fixed. And we took that latter approach. In fact, what I would describe the team that we'd assembled at GE, and even the team now at Menlo Micro Systems, it's really a team of willpower. It's wanting to will these solutions, figuring out through failure analysis. Why did it fail? How did it fail? And then go in and dig into it, invent around it, and develop these really new solutions, these new material systems, these new fabrication processes, the new designs, the new electrical circuits that are really part of the architecture that we're bringing to market today.
Was there a Eureka moment where you and the team realized we're onto something, this is the technology we should keep going forwards with?
Eureka moments, I kind of look at it as almost like, we had Eureka moments every year, almost every month. It was the first time we made the switch wiggle, right? We were high-fiving in the lab. It was like, oh my goodness, it's working, it's moving. We can see it moving under a microscope. Then it was, wow, we're switching a light bulb. Wow, we're now switching 1,000 watts. Oh my goodness, we've made a circuit breaker. Oh wow, that circuit breaker is switching 6 farads is protecting a 6 farad capacitor bank. Oh my goodness, we've now got a 3 gigahertz switch, a 12 gigahertz switch, a 28 gigahertz switch. These Eureka moments were really happening month after month, and it's just been this progression over the last decade plus.
How did you go about moving to higher voltages?
Yeah, so the first target that we had, and this is actually great leadership by the industrial business unit at the time. It's like, okay, 50 volts. It's like, show us what you got. Can you make that work? And it was all about the design. It was all about the ability of the switch to open, to close, to do it on time, to do it within this electrical circuit, right? It's like an orchestra of, in order to make a 50 volt switch work, you're not only mechanically opening and closing it, but you're shedding current. You're managing the voltage, you're managing the transients. And all of that had to be orchestrated within the device and within the circuitry that was around it and supporting it. And we're like, okay, great. Let's show this at 50 volts. And I remember we demonstrated it to the business unit at the time, and they're like, okay, great, fantastic. You got a couple months. Show us 200 volts, or show us 100 volts. Then show us 200 volts.
Oh no!
And it was like this never end. It was like this constant, increase and change of specs, which was, it was great. It was pushing the team. We were constantly having to reinvent, but really that taught myself and taught the team about cycles of learning. And that's really, from an engineering perspective, that's really what drives innovation. You don't get to the moon by saying, okay, I got to make a rocket and here's steps 1 through 10 bazillion that I've got to go through, and let's go through it and build it and put a person on that rocket and now send it into space. It's all these trial and errors. And that's really how, going back to the roots of Edison, Edison and GE, perspiration of cycles of learning, figure out what's working, figure out what's not working, and go back and learn and invent and try again. That's what we became experts at, I guess.
You mentioned that it's an orchestra of everything working together. When I was reading up on MEMS, I came across something that stood out to me, something about glass vias from Corning. When I think of Corningware, I think of like bakeware. How do they play into the engineering space, and how do they fit in with the MEMS work that you're doing?
So Corning has really been a great partner with first, with GE and with Menlo in developing this through glass via technology with us. For this switch, it is the interface to the outside world, and without a low loss, without in this case, a hermetic environment, a low loss hermetic environment, which these vias provide, our device our device needs a way to connect to the outside world. This protects it from the outside world, and it allows the communication kind of to and from the device. So it's the interface of this material science and innovation of the switch to the outside world.
I'd love to hear a little more about the whole process. The Menlo Micro website mentions a simple 14-step process. Is it simple in the context of semiconductor manufacturing being incredibly elaborate? Or can you unpack your process a little more for me?
Sure. Simple is, right, it's a relative term. And yes, the process is simple, meaning it takes fewer fabrication steps than a CMOS process. What we set out to develop and invent here was a platform technology. We wanted to develop both RF and power relays on the same platform. And to do so, we really had to develop a design architecture and a fabrication architecture to enable both. Right? When you think about the CMOS in industry today, the same processes, the same architectures aren't used for power and CMOS. They're completely different. In our process, in our device, we use the same unit cell. We use the same process flow. We use the same materials for a 28 gigahertz switch as we do for a 1 kilowatt DC switch. Same flows. And that is, when you kind of get down to the nuts and bolts of it, that's there because of the simplicity. We worked on the failure analysis. We worked on the materials. We developed the capability for this unit cell platform to be viable, to be a designable architecture across this range of DC to daylight.
Yeah, mixing power and RF, I think it would be considered crazy talk in most circles. What were some challenges you had trying to bridge that gap?
The challenges that really go back to the fundamental architecture and some of the early decisions. Do you make a switch and do you take a design that you really just focus on performance and say, you know what, I'm going to make the best 28 gigahertz switch? You probably would make some different choices. If you say, okay, I want to make a 1 kilowatt switch that's got to interrupt 1,000 amp fault current, you're going to make some different choices there, right? Different specs drive different outcomes. What we looked at doing was, how do we take these specs, these various specs and needs, and what architectures would we develop that we could scale? Because scaling is needed when you want to go to power. You want to be able to put hundreds to thousands of these unit cell building blocks in an array, in series, in a scalable architecture. In an RF component, you want to minimize coupling losses. You want to minimize substrate losses. You need to design your feeds and your traces and corners to not have RF signal leak out or be reflected. And so in the end, it came down to, you could actually do both with the same platform as long as we develop that initial architecture to be scalable in both series and in parallel. And then the traces and the interconnects really then dictate whether you're doing an RF design or you're doing a power design.
I'd like to shift a little bit. I'd love to hear more about the history of Menlo Micro. You've mentioned Edison a couple times, and I understand there's a connection there. Can you kind of give us a 10,000 foot view of the history of Menlo Micro and how you came to be?
Menlo Micro, and this is kind of an interesting story. How do you take a technology outside of a big company environment like GE and take that and commercialize it, scale it, and even how do you even get the processes going inside of a large company to allow this to happen, to justify it, to and then do the diligence behind it, and let alone what you then have to do to transition and start running a company. Ironically, it's never a one-time event. It's a series of events. And it's a series of, going back to this theme of willpower, between myself and one of the other co-founders, Chris Juvenel, it was really a matter of willpower. We felt this was the best thing for the technology. We felt that it was the impact that we knew we could bring to the world in terms of DC, AC, power switching, RF switching. We wanted to will this to happen. But in the end, it was a decision that was not ours, right? It was a GE decision. It really went through a series of events, and at first we actually looked at internalizing this within GE. How does GE in turn make a business out of this? And so we went through all of those checks and scenarios and even back down to tax implications of where do we put a fab and a foundry and the details of all that. there was one pivotal day, and ironically, I remember this day because it was the day that my daughter Paige was born. That was this pivotal moment, and it was a pivotal moment because we had a 8-hour meeting within GE of trying to, could we make this work inside of GE? And it was honestly on that day, December 15th, 2014, that tide shifted. There were too many roadblocks to internalizing this. And so that set off the motion of, okay, now let's really give some steam and some credence to the spin out option, which in the end, it was, how do we commercialize this for the GE businesses to leverage and use in the future? That was the goal. It was a process. And it took 2 years. Right? 2 years later was the birth of Menlo Micro Systems in December of 2016. To go through that process, and then how do we start a company, and how do we hire people? How do we put together an office and doing all the things that from a big company perspective existed already, and now we needed to figure out how to get all that infrastructure in place in something that was just getting started.
So you went from a company, General Electric, that had, according to the internet, over 200,000 employees, into a Spinoff that has maybe 50. Can you explain what that mental switch was like for you? No pun intended.
It was certainly transformative. When you're working at a big company, there's a process. When there's an IT issue, there's someone to call. When you need to purchase something, there's a process, and there's someone to work through with and to get that purchased. There's a business operating rhythm. When funding decisions are made, how programs are decided on, and what's reviews with the business units and the business leaders. Right, there's a business cycle. There's an operating rhythm. All of that doesn't exist, and so I think we did something really important when we started the company. We set the four founders, Chris Giovanello, myself, and then Russ Garcia and Jeff Ballin. When we sat down initially to kick this off, we really sat down and we first talked about not what we were going to do, but how we were going to build a company, how we were going to make this successful, how we wanted the culture of the company, the innovation that we wanted to, the innovative spirit that we wanted to culture, maintain. And I think it was really that aspect that's guided all the decisions that we've made going forward, independent of all the things that we had to do now that we didn't have that big company backing. And in the end, the way to achieve that and the way to build this up is when you've got a problem that's facing you, you go to the mirror and look in the mirror, and that's who's going to solve the problem. There is no one else. So buckle your seatbelt, get ready, look in the mirror, and talk to that person in the mirror about how you're going to solve the problem.
Well, my person in the mirror is telling me it's time for a quick break. We will be right back. Hey, we're sponsoring our own podcast. It's super meta. Now, I normally do this bit at the end, but I'm taking a moment to do it now because I know some of you skip the outro of this podcast. I'm not upset about that, just disappointed. But not too disappointed to give you a free mug. That's right, we have a ton of sweet Moore's Lobby mugs and other swag that we want to send to you. All you have to do is go to one of the Moore's Lobby social media pages and tag or mention someone that you think will like this podcast. Shout out to Peter and Brad and all the other folks who did that for the last episode. It's super simple. Go do it right now, and let's get right back to it. And we're back with Chris Keimel, co-founder and CTO of Menlo Micro. Chris, what was the state of the technology when you branched out, and where is it now?
When we branched out, it was not ready for commercialization. It could be used in high-value applications, and that's where we were using it within GE. It did not have the integrated packaging, the test infrastructure, the scalable wafer manufacturing that could expand the technology to other markets. We had to have a capable volume manufacturing fab. We had to have markets that we could go into, that we could grow with, that we could grow into. We had to reinvent the test architectures and the test platforms to test to make drive that cost of test down to a manageable and a reasonable level. It was really the scale up of all of these aspects, from the wafer manufacturing to the test to the design, the packaging. All of these had to be put now into commercial environments and having that commercial mindset, but also that the commercial infrastructure around getting customers, selling parts, developing new products. All that had to be put together, and that's what that transition was like, and that's what we had to put in play to take the technology from a low volume research fab and organization to a commercial organization that could support our customers and our business, because that's what we're about. We want to impact the world. We want to provide products that are order of magnitude impacting the wireless infrastructure network, impacting relays, bringing efficiencies, change. We have this rule of 99 that we call, right? How do we change how do we enable value for our customers with this rule of 99? Meaning, how can we make our customers' products 99% more efficient? How do we drive performance, improve that, make that performance 99% better? And that's what we're about, is creating those designs, those products, and those technologies, and the platform to deliver it.
In the context of the rule of 99, what makes a RF switch 99 times better, a power relay 99 times better? What are some of the things that really make people totally rethink how they're going to go about designing their products?
Yeah. And first of all, the way we make it better is that's our unit cell switch, our fundamental platform of a device. It's a metal relay on glass. You take the best of both worlds. You take your best conductors and your best insulators, merge them together. And from an RF perspective or a power perspective, that's your base platform to build from. And so right away, metals are more conductive than semiconductors, right? By the name of it, a semiconductor is a semiconductor. So right there alone, we have the technology is ohmic. It is a pure conductor. Because it's a pure conductor, because we're driving it through electrostatics and just moving charge back and forth, not driving current into a coil, not driving current into a leakage path, we are right then and there, we're orders of magnitude more efficient, meaning the power that you require to drive the device is nanowatts, microwatts to nanowatts versus milliwatts. And so there's a couple orders of magnitude right there. And what this translates to is efficiencies. Our customers gain that power back. They also gain in the sense of, like, from an RF perspective, being ohmic, our insertion losses are, again, an order of magnitude or more better than your typical gallium nitride, your SOI RF relays at frequency and also at power.
What does performance of a perfect switch look like? And where is the biggest gap between perfection and the reality of what's possible today?
Yeah. So right, when you talk to an engineer, nothing is perfect.
Right.
So we aspire to be perfect, but nothing is perfect. And that's where we came. That's why we have this slogan, right? The ideal switch. Right? It's not perfect, but it's probably about as close to ideal as we can get. And that's what we aspire to be. When you go and you talk to customers and what do they want, and this relates to every field. You go to a customer and you talk to and say, what do you want? They give you ideally what they want. Hey, I want this, I want this, I want this. And that's listening to the customer and then trying to figure out how do we deliver it. And we are trying to deliver that ideal situation with our switch technology by combining really the best of what the mechanical relay world has to offer in terms of kind of milliohm type of on resistances and isolation of an air gap isolation, combining that with some of the ideal features of a solid state relay, which is fast switching speeds, lower cost, smaller footprints, size, the size advantage, making these relays small and making them in chip form. that's from an ideal perspective, we're really combining the best of these two industries into our product.
It's safe to say that switches or transistors have changed the world in the last 100 years more than almost anything else. Where is the technology of switching going to take us in the next 10 years, 50 years, 100 years out?
Wow, 10 years, 50 years, 100 years. That's when you think about that, right? It's like, wow, that's a great way to step back and think about it. Like, wow, if I looked at that in the beginning and say, where would I be in 10 years, and where do I want Menlo to be in 10 years? Things change, things evolve. Where we want things to be, the switch architecture is about efficiency. It's about how do we drive efficiency and performance to our customers' systems. How do we make their systems more efficient? Because if we make their systems more efficient, we make the grid, all the way back, right? You can go all the way back to the grid, and the grid becomes less stressed, because there are switches everywhere. And so the potential impact that we have by reinventing the architecture of how we control power today, how we communicate power through RF, is at this fundamental switch building block. And so when you think about that now, and from a 10-year perspective, it's about building up. We are a spinoff, a startup. We are incubating, we're producing, commercially producing, but still incubating a technology platform. In these next 5 years, we're going to grow our RF business. We're going to work on these spaces of 20 gigahertz and 20 gigahertz and under, switching systems, control systems, incubating our power space on the AC/DC side, 1 kilowatt, 10 kilowatts, and really focus on those core architectures. Because that's, when you look at it, that's where there's a lot in the world. There's a lot of nodes out there that are in that space. And that's where we can have the impact. But we have an architecture and a platform that we can scale. So now when you talk about 50 years, 10 years, okay, we want to be close to 10 kilowatts, driving on to 50 kilowatts, maybe 100 amps. But we absolutely want to be, post 10 years and 50 years, we want to be driving the business in the power space to really where everything is controlled today, which a lot of those architectures are 100 amps, 480 volts and less. And that's really where we see this technology having a profound impact on enabling the re-architecturing and the gaining of efficiencies back through switching systems at those levels and under. It's driven by how we can impact, right? What are the big impacts that we can have? Efficiencies are huge. If you can make things 10%, 20% more efficient, that has tremendous savings on energy. And because switches are everywhere, the impact here is not just, it's not just on a product's efficiencies, but we're talking power plant and hundreds of power plants of types of efficiency type of gains, where you don't need these coal-fired power plants, or the draw on those and the need for those becomes reduced. And that's, when you talk about getting up and going to work every day, it's those types of big dreams that I know drive me and a lot of the employees at Menlo Micro Systems.
Random question. Is 28 gigahertz, is that a 5G play, like frequency range too?
20 gigahertz is 5G. You can call it small cells.
Okay.
When you look at where the architectures that are being developed for communication systems, and you look at where kind of the sweet spot is for small cells and distributed communications and higher data rates and networks, that's where we're seeing a need. And when you go beyond 20 gigahertz, sure. I mean, we can develop a 40 gigahertz device, a 50 gigahertz device, a 60 gigahertz device. But again, the impact is our switch has to go into a system. That system needs to be demonstrated. And so we're working with our partners at these levels and these integrated system levels at these frequencies. But we really see that right now these commercial systems, they've got to also be developing at the same time for us to develop switching products into that space. And that's why we talk about 20 gigahertz.
Yeah.
And when you look at most of the technologies, Today, most of the products today are 20 gigahertz and less. There's a lot of specialty applications that are higher.
It's coming. Yeah.
That's where that's where we're focusing, but it's not, by no means is it the limitation of our technology.
Okay. Interesting. If you got to spend a day doing R&D with Thomas Edison at Menlo Park, is there one thing that you would ask him or one technology that you want to maybe clue him in on about the future?
This was great because when I worked at GE, there were posters of Thomas Edison everywhere. I got to the privilege of walking by his desk that was at the Global Research Center. The part that I would want to talk to him about was maybe not so much about an individual innovation, but really his methodology. Because I think the methodology of innovation is what I love about Edison, and how he came to be such a prolific inventor, and not just a prolific inventor for the sake of invention, but for the sake of meaningful invention and meaningful products. I mean, we're living in a world today that was largely crafted by Edison and some of the other key people at the time in this electrified world. Really, it's just, I think it's that methodology. And I just love to understand if he would, if he could foresee how so many scientists, so many like myself and others, would be impacted by his methodology and really take his methodology to heart into what we do and what we bring today to the world of invention and commercial productization. But now, if I had to go back and talk to him about one particular thing, I would love to talk to him about electric vehicles. He was really focused on the electrified world, and he was seeing that transformation, right, into motors and into moving things, and was a leader in developing some of the base systems. And I would just love to see what his vision for an electric vehicle would look like, and then show him today's electric vehicles and what they are today, and just see what his response would be. I'm sure he would have all sorts of questions, all sorts of fun fun comments.
um, One of the pop culture debates is the Edison versus Tesla conversation, and Tesla has been portrayed as kind of this underdog visionary, where Edison has been portrayed as kind of this like industrialist. Can you give me your best pitch for Edison in defense of what he's done, and why maybe he's getting a bad rap in that conversation?
Okay, so they were both giants in their time, right? And they were just like any other inventor. You're putting forth your ideas. You're trying to convey what you think is the best solution, and we all have to, as an inventor and a scientist, you also have to communicate. You have to convince people that you're right, and that's part of being a scientist as well. Is communicating and letting the world know what you believe in. And so, honestly, both of them are giants in the field. They've had such a profound impact, and I would look at it from the perspective of they both had their impact. They brought AC, they brought DC, and we're leveraging today. Now, it may have been controversial at the time, but today and in the future, we're going to be leveraging all of their impacts. And so I actually, you asked the question to defend Edison, and maybe I think I'm actually defending both of them. I think that both of them were right. And I think that's the great thing about history is the times may cause a choice to be made, but we're living in a time now where we're inventing technology and going in the direction of both of those giants. And I think we have both of them to thank.
Oh, I love that answer. What what is the perception of the show 30 Rock, who famously parodied General Electric corporate culture?
Wow. No comment.
Fair enough. Well, sadly, we're out of time. Thank you so much for being on the podcast today. This was a blast.
Oh, Daniel, this has been such a pleasure. And thank you for all the questions and really helping to bridge between talking right here about Menlo microsystems, the ideal switch, the history of the switch, and where we think switch technology is really going to take us and transform the electrified world. But also this is a great venue that you've got here for bringing new concepts and industries to the perspective of engineers. And my hope and my wish and my dream is, you asked the question earlier about the 10 years, 50 years of where things are going to be. I'm wishful that the people who are listening to this podcast today are saying, wow, what can we do? How can we use this types of transformative technologies, and that they become the inventors that drive this technology and drive switching technologies forward.
Well, you heard him. Get to it. Thanks, everyone, for joining me today in the lobby. If you like this podcast, make sure you are subscribed to it in your favorite podcast engine. And also go to the Moore's Lobby social pages and tag or mention someone you think will like this podcast. We're sending out some Moore's Lobby swag to folks that do. I'm your host, Daniel Bogdanoff, switching off for this episode, but I'll catch you next time.